Well, yeah, thanks for having me and allowing some time for me to sort of walk through what Intellihot is doing in this space. It sounds like there's a lot of really exciting stuff coming. I'm particularly excited about the ASHRAE design guide. I know I spoke to a couple people at AHR this year about it, and it's very exciting. Excuse me. So, um, for those of you who aren't aware, I am with Intellihot. We manufacture commercial tankless water heaters. And today I want to sort of walk you through our newest product line that uses a CO2 heat pump for domestic water heating. Just skip through this initial slide because I think we're all sort of on board with why heat pumps make sense. But I think I want to start by talking about some of the challenges we've seen in conversation with design engineers and building ownership and how to get this technology implemented. And I think a lot of that has to do with there's maybe a gap in our ability to communicate the difference in heat pump water heater technology to building owners who are used to using a gas-fired or even an electric resistive heater. And in those cases, when you're using a traditional conventional water heater, you're used to putting it in the space and the water heater makes its own heat. And we're fundamentally changing that with heat pump water heaters. And that has thrown some building owners who would otherwise take the technology and implement it into a weird position where they're not entirely sure why we recommend putting equipment outside or why there's all these additional design requirements. So just walking through that list really quickly, I think some of those things are the fact that if you're putting equipment inside, you're going to have some amount of replacement heat because we're going to be moving heat away from the space. And so there's conversations about airflow. There's conversations about larger amounts of hot water storage than is traditionally necessary for maybe a traditional boiler system. There's also some conversation about what happens if the ambient conditions drop below a certain parameter, say it's cold weather outside, how are we going to make sure we're going to operate the system and still provide hot water? And then, of course, the question of how many do I need? How do I put them in the space? And is there incentive structure I can use to help pay for the equipment? So these are some of the conversations we have pretty frequently with building ownership. And then that bleeds over, I think, into the engineering design side. A lot of times engineers not having space allocated outside to design the equipment and having to try to fit stuff in a really small space with limited airflow. And so I'll just talk through our integrated tankless heat pump water heater and sort of explain how we've come across this design, where we're trying to solve certain problems with this and how we're thinking about it. And so just a high level first pass at it, I think when I say tankless heat pump water heater, that sort of begs an explanation because we all know that heat pumps are rather slow at moving heat, certainly compared to a piece of gas-fired technology. And so often when you say the word tankless as it pertains to water heating, that usually means no storage. And in this case, it doesn't exactly mean no storage. It means no potable water storage. So the idea here is to decouple thermal storage from the potable water that's being used at the fixture. And there's a few reasons for that, which we'll get into in more detail. But primarily, we know that there's some issues involved with storing large amounts of water, especially in the commercial space. I know Legionella was already brought up previously. That's one of the main concerns that we have. The way the system works on a high level is we've got our CO2 heat pump sitting on the top here, and we're going to move heat from the air. We're going to dump it into a thermal battery or just a giant thermal mass. And then we're going to use an on-demand heat exchanger coil where we'll pull our potable water through. And on my next slide here, or next couple slides, we'll go into more detail on how that works. So if I pull off the front cover and we look at the image on the left-hand side, what you're not seeing here is the vessel in which the thermal battery fluid is housed, but that thermal battery fluid is made up of a water propylene glycol mix. And so that mixture is going to be determined based on your ambient conditions and your particular geography. The heat pump's going to dump the heat into this thermal battery. We want to store very high temperature fluid at the top and keep it cooler at the bottom. It's going to have two resistive heating elements at 6 kW each for backup resistive heating. And then you've got this large stainless steel coil, which sits inside of that thermal battery fluid, and that's what's grabbing the heat. So if you conceptualize this sort of like an indirect boiler, we're just operating it backwards. In an indirect boiler, you would have your heat transfer fluid move through your coil. You'd heat up the water inside your tank. We're taking the thermal energy from the heat pump, we're dumping it into that thermal battery vessel, and then the coil is actually used for the potable water. That's where we heat up the water on demand. It does have a rainproof electrical enclosure. This is meant for indoor or outdoor installation, ability to interface with BACnet. There's also demand response integration. There's a port for a CTA 2045 module. So we can interface with all of those. We get into just a little bit more detail. Here's just a sort of a high level, quick schematic thrown together of how that thermal battery operates. It's sort of hard to see it just from a cutaway picture. The idea is that you've got cooler propylene glycol supply at the bottom of the tank. That's what's going to feed your gas cooler here. We dump the hot propylene glycol supply at the top, so we've got some stratification. And then you've got a coil where your potable water supply moves through to heat up your water with the two backup resistive elements here. And so as your building is using the water, it's being heated up, and then as necessary, the heat pump will turn on in order to recharge your thermal battery. If necessary, you've got backup electric resistive that will help maintain the state of charge in that battery at a high level. So one of the other concerns is that what happens when it gets cold weather? You have these cold ambient conditions that occur. How do we handle those? So there's a few things we're thinking about. First, we're making sure that the performance of the system down to very low ambient temperatures is robust. And so you see our third-party ambient to COP data here in the table in the middle of the screen. The other thing we're thinking about is knowing that this equipment is going to go outside. We've broken the country up into 7 sort of, maybe you call them ambient temperature zones. And we know that in certain zones, you're going to need a slightly higher concentration of that glycol supply to use as freeze protection. And so based on where the equipment is going to be shipped, there'll be a variable amount of glycol that gets charged up in the thermal battery, along with a glycol concentration sensor that makes sure we're always maintaining that level of glycol concentration. If not, then we would push a notification to the end user so that they're aware that something needs to be done here. Okay, and then, I just wanted to talk quickly about why a thermal battery is the approach that we're taking. And there's, I think, a few items here. First would be that having a thermal battery means you can actually store energy at much higher temperatures. So we're going to be storing much closer to 200 degrees, which actually reduces your required storage volume because you could pack more energy into that same amount of space. So if you compare the thermal battery with, say, a traditional hot water storage tank that's storing water at 140, we're about half the size with the same amount of energy. And so that helps to pack more equipment into a smaller space. It also means I decouple my building demand from my heat generation, and that sort of bleeds into our conversation about how we're going to handle temperature maintenance. Really, we want a product that's going to be very easily implementable. And so when you have a large building recirculation load, we'd rather integrate how we're going to handle that into our box rather than requiring some type of external system like a swing tank to handle that system. And so the way we're able to do that is because each individual unit would be independently controlled, you can then allow one of those thermal batteries to handle the recirc load. You keep the rest of the thermal batteries closed during that recirc period. And as demand increases, you could then open up your other thermal batteries and allow them to discharge so that you're trying to maximize efficiency rather than destratifying your whole bank of thermal batteries because of high temperature recirc coming back to the system. We're trying to think about ways to make that installation a little bit simpler, both for the designer and for the actual contractor who's going to be putting it in. And so then I'll say a couple quick pieces on sizing here and how we're thinking about sizing. We're aware that sizing these systems is actually pretty complicated. There's a lot of changing parameters, dynamic conditions that are going to affect how much water you're able to make at a certain time, both time of day and time of year. And in certain climates, those time periods are going to be longer or shorter. And so really, in order to do this properly, you have to have a holistic approach. And so we've thought about this a lot, and we've built our own sort of physics simulation that sits in a program that can be interfaced with the web app. So the web app allows you to input your sizing parameters, the same information you'd put in on a traditional hot water heating sizing tool. You know, how many fixtures do I have? Where am I located? And then we feed those dynamic parameters in, things like, what does my hot water usage look like over 24 hours? What does the ambient temperature fluctuation look like over that same time period? And then we simulate the heat pump and thermal battery performance over that 24-hour period, making sure we're iterating back and forth to make sure we have the optimal sizing, and then sending that as a report. And the high level of how that looks is something like this. This is sort of a simplified version of how it works, but in essence, your user inputs go to a lookup table that pick a couple of preliminary estimates, say based on historical sizing data, and then you input that into the dynamic model along with all of your, time varying parameters, things like ambient temperature, flow profiles, et cetera. And then you go through an iterative loop, making sure that, one, we have enough capacity, and two, we don't have too much capacity. That we're not carelessly oversizing the system, and then giving a range of options so that the engineer and the building owner can pick something that makes sense for their electrical infrastructure, for their, how much are they willing to spend up front versus annual operation. And so we're thinking about ways to make that a little bit more doable. And then lastly, I just want to talk about what scalability looks like. As we talk about larger and larger commercial systems, it becomes less and less viable to put 20 or 30 integrated heat pump water heaters into a space. And so the approach that we'd like to take is to say, let's take a modular approach where we put a series of heat pump decks outside, and that's what this unit here looks like, 6 CO2 heat pump decks, where you've got your energy from the ambient conditions that you can grab. And then you can pipe this low pressure battery fluid back and forth between a modular thermal battery system, which sits inside. And so your batteries and your potable water connections are always inside the building, and your heat pumps are going to be located outside. And then, of course, the beauty is that because you've got propylene glycol supply, that reduces your need for heat trace, even in climates where it's going to get a little bit colder. And you don't have to worry about refrigerant piping back and forth. This is low pressure battery fluid. And so that's allows a little bit of simplicity on design. Then I just want to point out too that the recirculation you can see is piped back to your cold water supply the same way you would with a traditional system, again by design, so that the thermal batteries will take care of the temperature maintenance rather than having to add an external system in order to do that. And with that, I am going to open up for any questions if anybody's got a couple quick questions. Otherwise, really thank you for your attendance and for the opportunity.
We did have a question in the chat, Robbie. Yeah. So about the heat exchanger. So is it a double wall heat exchanger, given some of the code requirements are going to need that? So
it's actually single wall, and here's why. That's a good question. We get that question a lot. It's a single wall heat exchanger. The Universal Plumbing Code allows a single wall heat exchanger in the event that you are using a food grade heat transfer fluid, so propylene glycol food grade, and that you're not exceeding the water, so that the pressure of your vessel does not exceed the water pressure. And so we're open to atmosphere, we're at atmospheric pressure. If you meet either of those conditions, single wall is allowed. I know that in some local jurisdictions, there's some extra, loopholes you have to jump through, and we're looking at those. And so certainly in those market segments, we're making sure that we're going to comply with all of the standards. So yeah, great question. Single walls is a big benefit because the heat transfer is so much, much more efficient heat transfer with the single wall. And so that's what we'd like to use.
Good info. Good question. Other questions?
You guys are going to go easy on me.
I have a question.
Sure.
Is the sizing tool available online for people to play with? Can you stick it in the chat?
I sure can. It sure is. So Yeah, please play around with it and see what you think of it. We're always open to feedback, and I will just drop the link here in the chat. We're always looking to add functionality. So yeah, your comments and feedback is welcome. Quick, we got a couple more in the chat. I'm just going to try to blast through. What temperature is at the top of the thermal battery was the glycol percentage? Yeah, so the top of the thermal battery we're storing at 190. And the glycol percentage will be a function of where you're located. By default, if it's what we would call maybe a mid or a moderate climate, it ships with 5 gallons of glycol. So that's somewhere around 8 or 9%. Is the product offered in specific discrete capacity options or the sizes are custom scalable? Yeah, so the way we would deal with scalable sizes would be by using multiple units to meet capacity. So you'd walk through our sizing calculation, and then we'd give you a number of units. We do have an approach where we say, if you're using a little bit more resistive backup, say during your peak loading conditions, you're going to use a little bit more resistive to help you get over those humps, then you can install less equipment. But then, of course, the penalty you pay is operational cost is going to go up, on an annual basis. So we do run a little bit of that calculation. So I hope that helps.
Okay, excuse me for a second. Hey, Ann Yardley, you have your camera on. Can you kill that? Thank you. Sorry, Robert, go ahead.
No worries. And it looks like Jill had a
and
question.
You're good on time. Yeah, you're good on time too. You have 11 minutes.
Oh, good.
So.
Good. Excellent. Okay. So I'll slow down. Jill says, can this be applied to baseboard heating? And the answer is, if you've got a project you're looking at, we'd probably be willing to take a look. Right now, we're focused on potable water heating, but I hate to say no to applications if they, if you've got something interesting. So we're always willing to look at things, and we're always innovating and adding new things to our repertoire. So, Jill, if you've got something to look at, we'd be happy to do that. Yeah, and I absolutely will drop my email down here so that you guys have my contact here. I'll also drop our applications team general email here. If you send to the applications@intellihot.com, that goes to our team of applications engineers specific to these types of projects.
Hey, Robbie, a quick question. You showed the different options on that slide with different capital expenditures being lower if you had more electric resistance. Yep. Are you finding that clients are going for lower CapEx and higher OpEx, or vice versa? Is it just a mix? What's the?
Yeah, that's a great question. In almost every case thus far, it has been the most CapEx effective product selection that we've seen, and I think that is likely to continue. Even what we've seen from engineers is that most heat pump systems are sort of a hybrid between a heat pump and electric resistive. There's very few pure heat pump systems, but excuse me, certainly we have that option if that's something that somebody's looking for. But so far, it's been that best upfront cost option that people have gone with.
And does the COP reflect the electric resistance, or is that just heat pump only?
Yeah, so the COP that is listed is, I believe, that is system COP, but that, of course, would be a function of how often your elements come on. So actually, I should verify whether or not that's the case, if that's system or if that's just the heat pump COP.
The published COP is the IE1 standard. So the electron comes in 3 flavors: IE1 standard with no electric elements, IE1 mid with 1 electric element, and IE1 max with 2 electric elements. The published COP is for the standard model.
Yeah, so I was incorrect there. It is just the heat pump side for the IE1.
Okay, thanks. That's helpful. I see a question from Bill Lyons. Bill, do you want to ask about your timeline question?
That was just on that, I guess, second or third from the end slide where you had multiple compressor's outside and the tank's inside that one.
Mm-hmm.
Is that it says next generation. I'm assuming that means it's in the future, or is this available now?
Yeah, it's a future product.
And is that months away, years away? Any ability to say when you think it'll come out?
So Bill, the thinking is, for most of the opportunities that we are seeing, we can use our IE1 product as is, right? We can cascade 6 of them together for projects, and the IE6 and IB3 are looking at much larger projects like a 500-room hotel or so. And just looking at the business side, we see a lot of the projects can use IE1 as is. Our timeline we are thinking is by HR next. We did show this off at HR this year. We'll continue to show this and gauge by the interest in the customers. There is certainly some interest in the New York area for this, and we are developing this product ongoing.
And checking my understanding here, so the existing unit all-in-one can be outside, but is that true in a freezing climate?
Yes, it does come with the heat trace, there are certain restrictions on snow level of snow that the pad height and certain considerations for lower ambient and high snow conditions. Other than that, that is also approved for an outdoor install.
Okay, but the next gen seems to be ideal for a cold climate.
It's more for a larger application, I would say, than climate. As you can see, 6 of them will be oversized for a 20-unit apartment, right? And looking at the sizings that we're seeing and the general market sense is that we would launch it probably in Q1 2025 when it will be ready for Q1, Q2 timeframe, just to get a general sense for, I think that's what you're looking for, right?
Thank you. Yeah, that's very helpful. Yeah, thank you.
And regarding there's one more question about the electric elements and when they come on. There are 3 different models. So if the jurisdiction does not allow for resistive elements, you would simply pick the IE1 standard, which has no elements. And there is a CTA 2045 connection. So should the grid, so it would be grid enabled. And if the grid has load shed or any emergency, we would not turn on the elements.
Yeah, and Shiva, is it accurate to say that also if you wanted to have the backup elements on board, you could still, in those particular climates, you could purchase the IE1 Max. There is an operational mode which would keep the elements from running.
That's
correct. An accurate
statement? So there are options in the display that you can force it to not run under normal conditions.
Okay, good.
Great questions. Thank you.
Thanks, guys.
This type of dialogue, I think, is very useful for both the manufacturers and our members.
So, Robbie, you got another question. You want to take that?
Oh, did I? I closed yeah. Do the units have scheduling capabilities to reduce operation on peak? Yeah, so we do have an operational mode that we are looking to implement that would allow the unit to learn your building usage, and it would charge up the thermal battery in your low peak conditions, maybe when you've got a lot less usage, and then be able to discharge or I guess load up for those big peak conditions. And so we do have that integrated, and that would be something that could be used for that, Daniela. I hope that answers your question. If not, please let me know. But in terms of trying to reduce operation on peak, absolutely, we would. That part of our commitment to the demand response is to use electricity when it's the cheapest, so that we're benefiting the customer and the grid as much as possible.
Okay, and Tristan has his hand raised.
Hi, so this is Tristan at Skycentrics. It sounds like you have situations where you have a lot of these in series or in parallel, more than one unit, let's say. Do you supply a controller, obviously, that manages many units, and do you put the CTA 2045 port in each unit, or do you have a CTA 2045 port in the controller? And the reason I ask all this is we would be interested in controlling and staging different units to come on at different times. If when you have multiple units, we just see it as one big unit, that would be more challenging for us. Do you have any thoughts on that?
Yeah, so Tristan, the way we approach staging is similar to the way we use our gas-fired technology. So, and that's to say that we take a masterless cascading approach, meaning each individual unit will have its own controller rather than having a master controller. And what that allows us to do, there's a couple benefits to that. I think the first would be that it reduces your single point of failure. You know, if your master controller goes offline, you can't communicate. That's a problem. But it also allows us to have essentially the units have dialogue with each other, so that if one unit needs help, it can kick another unit in the system to open up and help it meet that capacity. And so we would take a similar approach here. In fact, that's how our cascading technology works. It's masterless. If one unit needs help, it's going to determine which unit in the system has least amount of usage. It will prioritize kicking that one on so that we're balancing the load across them. And then same thing on the demand response side. So looking to allow the system to decide how the units should stage.
Okay, so that's super cool. Right, and then just a quick follow-up. So I'm pretty sure you do have a CTA 2045 port in each unit, right? So
correct.
If we want to communicate, and then are you guys pretty accurate at giving kind of that storage capacity number and your power usage number both? So in other words, when we're watching the storage capacity number, we see it cooling off, and you say, hey, if you load up right now, you're going to get, you're going to put in X number of watt hours into this unit before it's fully loaded. And the last question follow up is, do you have an advanced load up feature?
Yeah, yes, we do. We do. And yeah, that is how the system would work. So
awesome.
yeah, absolutely. Great question, Tristan. Yeah.
Maybe one last quickie. What's the smallest use case? You may have mentioned this before, Robbie, but
Yeah.
What kind of building would be the smallest that these would be adept for?
Sure. I'd say if we're talking really, really small, we've seen some interest in like the high-end residential markets, a really big house with, many bathrooms. But in the commercial market, we'd say the mom and pop restaurant shops. We've seen small schools have interest, office buildings, places where your hot water load is relatively small, but you can put one of these systems in and handle that load very effectively. And so pretty much as low as the commercial market goes, we've got, the IE1 would be a solution for that. You may even want to use the IE1 standard for that application where you just have the heat pump, because you may not even have the need for the elements in those cases. But we would certainly be able to size that and determine what makes the most sense.
Well, thanks so much.
Yeah, thank you. Tristan, I might have time for your question here. I think are we still good on?
Just a quickie, which was the smallest was great. What's the most number of units you've put into one building?
So we've sized projects that go very large projects. So we're talking very large lodging, hotels, multifamily. In terms of implementation, we've seen a middle school be a really good application type. There's also a multifamily complex on the East Coast that's purchased some units and is putting them in. I think that application has 9 or 10 of them. It's a pretty large load there. But certainly we're capable of going very large. That's the idea here. We play, solely in the commercial market really, and so everything we do is sort of oriented up towards those larger applications. It's just a function of how many and how do we make it work. And that's where I think that applications team we have in-house does a really good job of working with engineers. So if there's an interest in something, we'd be happy to look and see if there's if we can make something happen and how we would implement it.
Thank you, Robbie, and thank you, Siva, for joining us today and tag teaming all the great questions we had.
Absolutely. Thanks for having us, guys.